This is a piece of uranium ore. On its own, it's not particularly dangerous. You could hold it in your hand for a moment and be fine, but with the right engineering, this rock can power a city for decades, or destroy one in a heartbeat. The difference between a useless rock and a world-changing fuel is a process called enrichment. Today, we're going deep. We aren't just talking about spinning things. We are looking at the molecular physics, the massive industrial complexes, and the sheer geopolitical weight of uranium-235. By the end of this video, you'll understand exactly how we take dirt and turn it into the most energy-dense material on the planet. To understand enrichment, we have to talk about isotopes. Natural uranium is mostly U-238. It's stable, boring, and won't sustain a nuclear chain reaction. Only about 0.7% of natural uranium is U-235, the fissile version we need for power. The problem: U-235 and U-238 are chemically identical. You can't use a chemical reaction to separate them. The solution? Mass. U-238 has 3 more neutrons than U-235. Enrichment is the art of exploiting that tiny difference. You can't just put rocks into a centrifuge. First, we need to turn the uranium into a gas. Uranium ore is crushed and treated with acid to create yellowcake, U3O8. The yellowcake is reacted with fluorine to create uranium hexafluoride. Engineers call this hex. It's a strange substance that is solid at room temperature but turns into a gas when heated slightly. Fluorine only has one stable isotope, so weight differences are strictly from the uranium. This is the heart of the operation. If you've seen photos of enrichment plants, you've seen rows upon rows of tall silver cylinders. These are gas centrifuges. The UF6 gas is pumped into a vacuum-sealed rotor spinning at supersonic speeds. The slightly heavier U-238 molecules are pushed toward the outer wall. One centrifuge only enriches the gas by a tiny fraction. To get to reactor-grade levels, we connect thousands of them in a cascade. Enriched output feeds into the next machine in a continuous loop. Centrifuges weren't always the king. During the Manhattan Project, we used gaseous diffusion. Diffusion involved pumping gas through miles of porous membranes. It used a staggering amount of electricity, enough to power a small country. The Calitron used magnets to bend a beam of ions. It was incredibly slow and expensive, but got the job done for the first atomic bombs. This magnetic separation was pure physics in action. Not all enriched uranium is the same. It depends on what you want to do with it. Natural uranium is just the raw material. Standard plants need 3 to 5%. Advanced reactors need HALEU up to 20%. Anything above that is highly enriched, used for submarines and research. The work required to get from 0.7 to 4% is actually much harder than going from 4 to 90. This is why non-proliferation experts get nervous once a country reaches even 5%. The hardest part is over. Once enriched, the gas is turned back into a solid powder, pressed into ceramic pellets, and loaded into fuel rods. Those rods will sit in a reactor for years, providing carbon-free baseload power. It is the fuel for a cleaner future. Enrichment is one of the most guarded secrets in the world. It's a tool of immense power, and like all tools, its value lies in how we choose to use it. This is Simple Guian, signing off.